Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 1. Limits and Continuity. Section 2.2. The limit of a function.
Lesson 3. Limits that go to infinity.
Okay, so our next topic is finding limits that go to infinity. What do we mean by that? Well, that's what we're going to find out in this next segment. Let's look at this particular example. We're going to try to find the limit as x goes to 0 of 1 over x squared, that particular function. Well, to find that limit, let's start by asking the following question. What's the domain of the function we're looking at, 1 over x squared? Remember that this is a rational function, and for a rational function it's defined everywhere except where the denominator is equal to 0. Well, what would make this denominator, x squared, equal to 0? That would be true only if x itself is equal to 0. So the domain of this function, the answer to this question, is all real x not equal to 0. So the only value of x that we can't put into this function is 0 itself. Well, remember that when we're finding a limit, we're not too worried about what happens at x equals 0. We are only concerned with what happens as x gets close to 0 for this function 1 over x squared. So we can still ask a question about the limit as x goes to 0, even though the function is not defined at 0. Well, we're going to try to find the limit of this function by graphing it. So my next question is, what happens to the graph at x equals 0, that place that's not in the domain of this function? Let's go ahead and try to figure out the graph by putting in a few values. So I've drawn a table over here with x's in this column, y equal 1 over x squared in this column, and I'm choosing x values that are getting successively closer and closer to 0. I'm going to put in 1, a half, a third, a fourth, a fifth, and so on. Notice that these x values are approaching 0 through values that are a little bit larger than 0. So I'm going to put down here that we are allowing our x to get closer and closer to 0 through values that are a little bit to the right of 0. So we're really approaching 0 from the right-hand side. And later we'll worry about what happens as x approaches 0 from the left-hand side. Well, let's go ahead and see what our y values are for each of these x values. When x is equal to 1, y is equal to 1 over 1 squared, which gives me an output value of 1. So now let's try putting x equal 1/2 into our function. Well, if I replace x with 1/2, I'll have 1 over 1/2 squared, which would be 1 over a fourth. And when I invert and multiply, that would be 1 times 4 over 1, or 4. So I get 4 as an output. If I put in a third, similar, I'd get 1 over 1/3 squared, that's 1 over 1/9. When I invert and multiply, I'll get 9 as an output. If I put in 1/4, in a similar way, I'll get 16. If I put in 1/5, I will get 25. And notice that these input values are getting smaller and smaller. They're getting closer and closer to 0 through values to the right of 0, values that are a little bit larger than 0. And what's happening to the output values? I get 1, and then 4, and then 9, and then 16, and then 25. You can see that if I put in 1/6, that'd be even closer to 0. I would get 36. Well, if you're not sure what's happening to these outputs, let's go ahead and look at the graph. When I put 1 in for x, I get 1 for y. Notice this y scale is crunched. So I go over 1 on the x-axis, and 1 on the y-axis is just about here. When I put in 1/2 for x, I get 4 as an output value for y. And again, because the scale is crunched here for the y-axis, I go up just a little bit. When I put in 1/3 for x, I'm getting 9 as an output. When I put in 1/4, which would be about here, I get 16, roughly here. And when I put in 1/5, which is pretty close to 0. I'm getting 25 as an output. If I were to put in 1/6, I would get 36, which is already going off the scale of my y-axis. Let's go ahead and connect these with a continuous curve, assuming my function is continuous through these x values. And I get something like this. And we can see from the table what is happening to the output values. It looks as if they're getting just larger and larger. If I put in 1/10, which would be very close to 0, I would get 100 for my y value. So it appears that these y values are getting larger and larger. Well, let's see what's happening in terms of our limiting process. We were asked to find the limit as x approaches 0. We're doing 0 from the right-hand side for the moment. We'll talk about the limit as x approaches 0 from the left in a minute. And if we used our graphing technique, we say, well, when we put 1 in for x, we get 1 as an output for y. When we put in 1/2, we get 4. When we put in 1/3, we're going to hit 9 on the y-axis. When I put in 1/4, I'm getting 16. And when I put in 1/5, I have to go way up to hit the curve, and I'm getting 25 as an output value. Now, remember, for the limit as x approaches 0 from the right of 1 over x squared to exist, the output values, as we get closer and closer to 0 from the right, the output values associated with those inputs have to be collecting around one number on the y-axis. Is that happening? Well, no, unfortunately, the y values are not collecting around a single number. They're actually just getting larger and larger and larger. The closer I choose my x to 0, the farther up I would have to go to hit the purple curve here, which is really a hyperbola. So the outputs are not collecting around a single number. What does that mean about this limit as x approaches 0 from the right? It means this limit does not exist. The y values are not collecting around one number. However, in this particular example, the outputs are getting larger and larger and larger, so the limit doesn't exist in a very particular way. The outputs are going towards positive infinity. They're just getting larger and larger and larger, 1, 4, 9, 16, 25, and so on. So oftentimes what we write is that this limit, as x approaches 0 from the right of 1 over x squared, we say that the limit equals positive infinity. Well, what does that mean? Infinity is not a number that you reach. What we are really saying is that the limit does not exist in a very particular way. It doesn't exist because the outputs are getting infinitely large, larger and larger and larger as x gets closer and closer to 0 from the right. So we write positive infinity, or you can also write just infinity. If we don't put a sign in front of it, we assume you mean positive infinity. But it's really a way of saying that the limit does not exist. And for this particular type of limit, we will always write positive infinity or infinity rather than does not exist. We try to be very specific about how the limit doesn't exist. Well, if you want the limit as x approaches 0 from the left, you could do the same type of thing where you allow your x values to approach 0, but now through values that are negative, values that are a little bit less than 0. And you can check yourself that the graph you end up getting is very similar. It's actually the reflection of this graph across the y-axis. That's because this particular function, y equal 1 over x squared, is symmetric across the y-axis. It's an even function. So if we were to graph this for negative values, -1, -1/2, -1/3, -1/4, -1/5, things getting closer and closer to 0 from the left, you would end up with another half of the graph which looks just like the right half. If you were to fold the paper right along the y-axis, these two halves of the curve would actually match up. Now, let's see what the limit is as we approach 0 from the left. When I put -1 in, I will get positive 1 as an output value. If you put in -1/2 for your x value, you will get positive 4 again as your output, and so on. If I put in negative 1/3, I will get 9. If I put in negative 1/4, I will get 16. If I put in negative 1/5, I will get 25 again. And we can ask the same question. For this limit, as x approaches 0 from the left through values that are a little bit less than 0 of 1 over x squared, we have to ask, are the outputs collecting around one single number on the y-axis? They are not, and so the limit again does not exist. But how do we write that? Well, it appears that the output values are getting larger and larger and larger the closer I get to 0 from the left-hand side. So we could go ahead and say again that the limit is positive infinity, or simply infinity, and that's a particular way of saying that the limit does not exist. It's saying how the limit doesn't exist or why it doesn't exist, and it's because the outputs are just getting larger and larger. Well, what do we say about the overall limit? That's what I was really asking at the beginning of this example. What's the limit as x approaches 0 from both directions? Well, the limit does not exist because the outputs are getting larger and larger. And in this case, because the outputs are approaching positive infinity, just sort of screaming up towards larger and larger values as we approach both from the right and from the left, since they're approaching this same infinity, as a final answer, we say that the overall limit as x approaches infinity of 1 over x squared is positive infinity, or again, if you want to, you can write or infinity. And again, that means that this overall limit also does not exist because the y values are just getting unboundedly large as we get closer and closer to 0 from either direction. Well, in general, we write down the following definition for this kind of limit that goes to infinity. We say that the limit as x approaches some finite number a, in our case our a value was 0, of f of x, is equal to infinity, or again you could have written positive infinity if you want to be very specific, if the values of f of x can be made arbitrarily large, in other words as large as we please, by taking x sufficiently close to a, but again not equal to a. So again we're allowing x to approach a but never quite get to a. Well, again, what does that mean, arbitrarily large? It just means that the y values can be made as large as we like. The outputs can be forced to be as large as we like by choosing x values that are close enough to our a value. So by taking x sufficiently close to a. And just as we did in our definition of the limit earlier, where the limit was some finite number L, we specify that we don't care what happens when x equals a by saying but not equal to a. So x close to a but not equal to a. Okay, great. So now let's go ahead and just find the limit of a couple of other functions from the graph. In the next section, by the way, we'll be talking more about finding limits from the equation rather than from the graph. But this section we are just trying to learn about the idea of a limit, and that's much easier, I think, to get from the graph rather than the equation. Okay, so let's look at this example here that's at the top. We are asked to find the limit as x approaches 4, so we are approaching 4 from both the right and the left, of this function g of x, whose graph is shown here. Well, let's go ahead and see if we can find that limit. If I approach x equal 4 from the right-hand side, let's see, if I put in something like 5 as an input value, I have to go down to this graph and over to get my corresponding y value. So this would be the y value f of 5. Oh, I'm sorry, g of 5. See if I could change that to a g. If I put in something closer to 4, like say 4.5, and you notice that I have to go farther down to hit the graph and then go over to the y-axis. And so I'll get some output value here, which would be g of 4.5. If I choose something even closer to 4, I have to go down farther before I hit the curve and then over to the y-axis. And if this curve continues down this way with a vertical asymptote right at x equals 4, the closer I get to 4, the farther down I have to go to hit the curve, and so the lower down I will hit on the y-axis. So if we were to look at the limit as x approaches 4 from the right of this function, what would we say? Well, the limit does not exist. The y values are getting smaller and smaller. They're getting large in the negative sense, large in absolute value, but negative in sign. They're actually marching downwards towards negative infinity. So the limit does not exist, but we can go ahead and specify in what way the limit doesn't exist by saying it doesn't exist because g of x is screaming downwards. The output values are getting smaller and smaller. Really, we sometimes say large negative values, meaning large in absolute value, but negative in sign. So we write the limit as x approaches 4 from the right of g of x is equal to negative infinity. If we approach 4 from the left-hand side, say I were to plug 3 into my function g of x, it looks like if I hit the black graph and go over, I get an output approximately here. If I chose 3.5, that's closer to 4, but a little bit less than 4, I would end up getting a value something like this as an output. And it looks as if the closer I get to 4, again, the farther I have to go down to hit the black curve. And so again, I'm getting output values that are marching downwards towards negative infinity. So if I were to write what's the limit as x approaches 4 from the left-hand side of my g of x, again, that limit does not exist because the outputs are not collecting around one single number on the y-axis. But I could again write that it doesn't exist because the outputs are going down towards negative infinity. What would I write down for the overall limit then of my function? If I want the limit as x approaches 4 from both directions, the right and the left, well, since these are both the same sign, they're both negative infinity, what we are saying then is as we approach 4 from both directions, the output values are approaching negative infinity, and I would simply write that the limit does not exist because the outputs are approaching negative infinity, and we express that by saying the limit as x approaches 4 of g of x equals negative infinity. Again, it's a specific way of saying the limit does not exist. Alright, well, I'd like you to stop the video and see if you can do this example that's down at the bottom of the page here, and then we'll go ahead and do it together. Okay, so hopefully you've had a chance to think about this one. Again, what you might want to do is first think about the limit as x approaches the number negative 3. We are asked to find the limit as x approaches negative 3. You notice it doesn't specify the right or the left, and so that means we want the overall limit. We want the limit as x approaches negative 3 from both the right and the left. And so what I'm going to do is find the limit as x approaches negative 3 from the right of h of x. So we'll try to do that one first. And if you were a little bit confused because this happened to be a negative value that x was approaching, remember the negative is in front of the 3, and so it's really x approaching negative 3 in general from both directions, and we are now looking at x approaches negative 3 from the right, so through values from the right. If you had trouble with this particular one, you might want to now stop the video again and look at each of these limits separately, the limit from the right and the limit from the left, and consider them separately. But let's go ahead and do this together now. If I choose a value that's a little bit to the right of negative 3, say negative 2, something like that, I have to go up to hit the curve, and I go over to the y-axis. If I chose something like negative 2.5, that would be a little bit closer to negative 3, I have to go higher to hit the curve, and so I get a y value that is larger. The closer I get to negative 3 on the right hand side, the higher I have to go to hit the black curve. And so you notice that the y values are marching upwards towards positive infinity. And so I could write the following. I could say the limit as x approaches the number -3 from the right-hand side of h of x is equal to positive infinity. Again, that means that the limit does not exist because the y values are not approaching a single number. They are just sort of screaming upwards towards positive infinity the closer I get to -3 from the right-hand side. Okay, let's try finding the limit as x approaches -3, but now from the left-hand side of h of x. So hopefully you gave this a try. If I plug in something like -4 for my x value, I have to go down to hit the black curve and over to the y-axis. If I choose something like -3.5, I have to go farther down to hit the black curve and then over to the y-axis. The closer I get to -3 from the left-hand side, the farther I have to go down to hit the black curve, and so my output values, my y values, are getting smaller and smaller. Or another way of saying it, sometimes people say they're getting larger and larger in the negative sense, larger in absolute value, but a negative value. So what's happening then to this limit? The limit as x approaches -3 from the left, the output values h of x are approaching negative infinity, and so we write the limit is equal to negative infinity. Again, it's a way of saying that the limit does not exist because the outputs are not collecting around a single number but are approaching negative infinity. Well, we were really asked to find the overall limit. We were asked to find the limit as x approaches -3 from both sides. And you might wonder what the convention would be in a case like this, where h of x is approaching positive infinity as we approach -3 from one direction, and yet it is approaching negative infinity as we approach -3 from the other direction. And some people might guess, well, you'd write down that the limit does not exist because h of x is approaching plus or minus infinity, meaning it approaches one infinity from one direction and another infinity from the other direction. But we never write it that way. It's just convention. Everybody agrees on a standard convention. And in this case, we simply say that the limit does not exist. It's because these two infinities are not equal to each other. They're not the same infinity. One is a positive infinity and one is a negative infinity. So if these two things don't match up, we simply write that the overall limit does not exist. If the two infinities do match up, like they did in the case up here, these are the same infinity. It's a way of saying it sort of informally. They're both going towards negative infinity. Then we write negative infinity for the overall limit. If they don't match up, we simply write does not exist. Okay, that concludes our first introductory section on the limit of a function. In the next section, we'll look at how to calculate limits not from the graph, but or a table, but just straight from the equation, and we'll learn several different theorems that allow us to find limits rather easily from